Imagine trying to find out the volume underneath a function. One thing you might do is find out the volume of one of these slices, and then just find out the volumes for the slices after it. And so what you get is the volume underneath the function after you summed up all of these volumes. If you guys like the animations, feel free to like and sub and drop a comment, because I don't know if I should keep doing the whiteboard or keep doing the animations or do both. All right, so feel free to comment on that. Now, let's say that my function right over here for the surface, so recall that this is a three-dimensional function, right? 3D function, where you have two inputs, an x value and a y value, and then that's gonna give you a z value, which corresponds to the height, right? So for, let's say, an x value here and then a y value here, well, that's gonna correspond to a height up here. And so what is the area of this thin strip, right? What is the area of this thin strip, the first strip that I've drawn out here? What is the area of this? Well, this is just going to be the integral of our function, right? F of x comma y, right? Dx. And so what this is saying is that, well, for every tiny step that I take in the x direction, or a tiny step that I take in the x direction, dx, I'm going to multiply by the height, right? The height is going to be, in this case, it's going to be like whatever this is. And then after that, I just multiply them together to get this rectangle, right? To get the area of the rectangle. And I keep doing this for every dx, right? I move another step, dx, across this surface. Another step, dx, right? Another step and another step. And then so as I make more and more rectangles to approximate this area, well, I'm going to get more and more accurate. But in order to get the full surface, right, the volume underneath this full surface, well then what I have to do is I have to take this entire integral, right, this entire area underneath this surface, and I have to multiply by dy, which is like a tiny step in the y direction. And so what I get is I get a volume. Right now that I multiply it by a tiny step in the y direction, I get this volume, right? A tiny step in the y direction, I get this entire volume. What we've essentially done is we take this integral and we keep multiplying by tiny steps, dy, right? Tiny steps, dy. We keep doing that. And so that's actually going to give us the volume of our entire surface. We take the area of one of these strips and we essentially sum up these areas along the y direction as well. And so we can actually rewrite this as the double integral of this integral right over here with respect to dy. And all this is saying is that we're essentially finding out the area of one of these strips, and in order to make it a volume, well, we have to multiply by a tiny change in the y direction. And we keep doing this, right? After we've gone to the next strip, let's say we've gone to the next strip, we find the area under that strip, right? And then we move another dy to make it a volume. And we keep doing that until we get the volume of the entire thing. And so one way to think about it is that you're effectively extruding the singular integral by adding another integral, right? And so this is just the idea behind double integrals. And of course, there's going to be bounds. Like, for example, it's going to go from the x integral is going to go from whatever these x bounds are, and the y integral is going to go from whatever these bounds are. But it's the same kind of idea, where in this time, you think about it as summing over an integral, which is the area. So you're summing over areas to get a volume, okay? Now, why settle for one interpretation when you can settle for two? Here's this simulation from Gemini. And so another way to think about double integrals is that if you're taking a tiny step along dx and then a tiny step along dy and multiplying by height, you actually get, well, a tiny rectangular block, right? In this formula right over here, what are we doing? It looks like we're multiplying dx, a tiny change in x, by a tiny, actually, let me just get rid of these things right here. What are we essentially doing? Well, imagine dx, tiny change in x direction, multiplied by a tiny change in the y direction. And if we multiply by the height, what are we getting? We are actually getting a rectangular prism, a rectangular block, right? And we're essentially doing it for every single bound, for our bounds, right? So from our x bounds, we are going to keep on computing like these rectangles, right? And then we're also going to do it for our y bounds as well. And so what we get is essentially, well, this approximation of the volume underneath our curve. And as we make the rectangles more and more defined, as we take smaller and smaller steps for our dx's and dy's, look at what happens. We have successfully approximated, or actually found in this case, the volume underneath our surface. As we make our rectangle smaller and smaller, dx and dy smaller and smaller, we get the volume underneath this surface. So that is actually another way to think about it. For all the steps, for all dx's along our x bounds, and then for all the dy's along our y bounds. So imagine if we have this function right over here, where x is from 0 to 2 and y is from 1 to 3, and we want to actually calculate the volume underneath this function from these bounds. And so the way we do it is, the calculations are actually not too bad. And so what are we going to get? We're going to get the double integral of our function, 3x squared plus 6y, dx dy. Okay, and you can think about this inner integral right over here, the inner integral as the area. And so to calculate the area, well, this integral has to represent the x bounds, right? And so our x bounds have to be from 0 to 2. And then this outer integral right over here essentially represents, trying to find a volume by taking another step in the y direction. And so this outer integral is going to represent the bounds for the y value. And so this is going to range from 1 to 3. And now you can just solve this like any old integral. Now, if we are integrating with respect to x, this 6y right over here would be treated as constant. So what you're actually going to do is, first let's just evaluate the inner integral. So the inner integral, let's just do that. So this inner integral is going to be from 2 to 0, 3x squared plus 6y dx. And so the 6y would be treated as a constant. This would be treated as a constant. So this would just be 6yx. And then this right over here would just be x to the third power, right? Because you add 1 to the power divided by 3. And then after that, this is going to be evaluated from 2 to 0. Now, when x is 2, then that's going to be 8 plus 12y. And then when x is 0, of course, this is just going to be 0. So we can just ignore that. And now this is going to be the result into our second integral. So our second integral is going to range from 3 to 1. And now it's going to be dy. And now we can evaluate it like so. And so this is going to be 8y plus 6y squared. And this is going to be from 3 to 1. And then now we plug in 3 into this. This is 24 plus, and then this is 6 times 9, that's 54. That is going to be 78. And you subtract this from plugging in the now that we found out the upper bound, we found out the lower bound. So we plug in 1 into our integral. So 8 plus 6 is 14. And 78 minus 14 is 64. And that is going to be our final volume. Okay, so that is going to be our answer. And here's the cool part about these double integrals. And the cool part is that you can actually swap the order. So instead of integrating with respect to x first, you can integrate with respect to y, and you would still get the same answer. So here I have it set up where instead of integrating with respect to x, now we're doing it with respect to y. So this integral now becomes the y bounds, which we previously had outside, and now we have it on the inside. And in the outer integral, of course, there's our x bounds. And so let's do it now. So let's do calculations. So this is going to be the integral from 3 to 1 of 3x squared plus 6y dy. Now that we're integrating with respect to y, we treat any x's as a constant. And so what we get is 3x squared y. And then all of this is going to be from 3 to 1. And so when we plug in 3 into these, what do I get? I get 9x squared plus, and then this is going to be 27. And I subtract this by, I like putting things in brackets. I don't know why. It kind of just looks cool. This is going to be 3x squared and plus and that's just going to be 3. And so when we actually do the subtraction, we get 6x squared plus 24. And now it's time to do our inner integral, which ranges from 2 to 0. And so what we get is now we're integrating with respect to x this time. So this one is just going to be 24x. And then this one is just going to be 2x to the third power. This is going to range from 2 to 0. 2 to the third power is 8. And that's going to be multiplied by 2, which is 16. And 24 times 2 is going to be 48. And when we plug in 0 into everything, it's just going to be 0. So our final integral has, whoa, isn't that pretty cool? Wow. So it looks like even when we kind of swapped the order, we still get the same volume. Of course, I feel like there's certain times where, one order might just be easier than the other order, but nevertheless, that's still pretty cool. And the reason why you get the same answer, remember that this right over here is the integral of our function with respect to x, right? So we're saying that essentially this is our x-axis, right? This is our x-axis, this is our y-axis. Sorry if these x and y's didn't seem clear, but there we have it. And so that is going to be the area for a constant y value, right? And then we just sum it all up, so we add in another integral. That's just a little review. Now, we could have easily just as, simply done this in the y direction. Instead of saying that we want to find out the area here, and then we can push it to 3D by multiplying by dy, what we can also equivalently do is we can say, oh, I want to find the area here. Right, I want to find the area here. And so this is the integral of f of x comma y dy. And then now to push it into 3 dimensions, well, now we're going to multiply by a tiny step in the x direction, dx. And so the order actually doesn't matter. It only changes the way that you extrude your, area to make it a volume, but it actually doesn't change the actual value itself, right? You're just changing the axis of which you are extruding, and that's why you get the same answer, okay? And that's actually something called, and it's like a little weird theorem that someone proved. That is called Fubini's theorem. Fubini's theorem. So that's a pretty cool thing that you can kind of swap the order of the integrals and you still get the same answer. And it makes sense intuitively.